Hello everyone, and today we're going to have our lesson on the electromagnetic spectrum, and more specifically, electromagnetic waves. So let's have a look at where we've been and where we're going. So this chart should look familiar. We've looked at it a couple of times. And now when we are looking, so we've talked really just about our mechanical waves, right? That's where we focused. We've mentioned electromagnetic waves, but we haven't really dived into what are they and how do they function. And now one thing with that, so up until this point, we've talked about mechanical waves can split into two parts. We can have a longitudinal wave, which is sound, and we can have a transverse wave, which is really every other wave. And this does hold true for our electromagnetic waves. So our transverse waves actually can be our EM waves as well. Now here's something I want to be really clear about. There's transverse waves that require a medium. So like when we shake a rope and we physically have that medium that wave is traveling through, it requires that medium to travel, because if we didn't have that rope there and we just swung our arm back and forth, nothing would really happen, right? And then there's those that do not require a medium, and that would be our electromagnetic. So it does kind of split a little bit there, and so I wanted to kind of make that piece clear here with this diagram. Electromagnetic waves, as far as drawing them, if we were looking like a sheet of paper, if we were to put them into like a 2D representation or something, they would look identical to our transverse waves, as far as they'd have a crest, a trough, amplitude, all of those things like we do in our transverse waves. So what are our electromagnetic waves? Well, electromagnetic waves are really just vibrations of the electric or magnetic fields. And we spent a little bit of time, looking at these during our electricity units and looking at magnets. So they're not sound, or they're not waves that are traveling through water. So yes, they're not water themselves, but they're not sound and they're not like water waves, things like that. That's what I mean by saying or water. Sorry if that's unclear. And one thing to think about too is all of our electromagnetic waves, so all of them really are light. And you could even actually add this further and you could say they are all radiation, because they absolutely are, because light is radiation, which we'll talk about in a little bit in detail. We just can't see all of them, right? So just because we can't see it doesn't mean it's not light. We actually see an incredibly small piece of that light. And in that animation in the upper right hand corner, it'll quick pan through all of the different types, and you'll see the only one that we see is the part labeled visible. And that actually makes it look bigger than the part we actually see. And we'll again spend looking at the sizes of these waves, we'll be able to identify that even more. Waves travel through particles, particles is maybe not the greatest word to use, but called photons, which is basically massless energy. They're like these packets of energy, but they don't have any sort of like test weight. We can't put them on a scale and really measure their mass, so they are just deemed as massless, and it's basically just energy that interacts with these magnetic fields that exist all over, okay? You can think of the magnetic field kind of as the medium of the electromagnetic waves. Now, they don't require a medium when we say that. And of course, medium implies something, a physical substance for it to travel through. But if you can, just to kind of wrap your head around it, if you think of those electromagnetic fields that we've spent time talking about, a magnetic field as kind of the medium that an EM wave travels on, that's fine too. So you should have this chart available to you. You'll fill out the information in here, and you need to put in the wave name. So I'll give you the name of the wave and you'll fill it out. The other thing you need to do is record the size or size range, kind of the general bracket it would fall in. So you can say, okay, that's going to be a wave that has a large size, one that's small. And when I say size, to be specific, I'm talking about the wavelength of that wave, the actual size of those waves. Then you're going to identify some uses, what things make it, and then what are some possible dangers that these might have. So let's start it off with a radio wave. So we're going to actually start with the biggest wavelength wave and go to smaller ones. So the general average size is roughly 1,000 meters or 10 to the third meters. They can definitely be a little bit smaller and they can definitely be a little bit bigger. I think they can kind of even go from like I think, roughly, 1 meter to 2 kilometers. It's a really big range, but this is that fair average about where it is a typical radio wave. It does depend on the radio signal for that size, but the general average is, that 10 to the third meters, or about 1,000 meters. Another way to think of 1,000 meters would be a kilometer. Common uses, by far, communication, right? You think of your radio in a car or any of those types of things, cell phones, any of those things that really are, a lot of those wireless communications are using radio waves to communicate. A lot of things make them, of course, a transmitter, right? An antenna and things like that are trying to receive any sort of signal given off by stars. Absolutely. Sparks, lightning gives off a lot of those. And this is why you may hear static on your radio during a storm, or you get some of that interference, or maybe if you have TV through like Dish or something, some of those will cause that because it causes interference with it. So a lot of those things giving out those radio waves can cause interference, and provide reduces the quality of the signal. So that's where a lot of that's coming from, because there's a lot of radio waves all over the place that you may not realize about because we can't see them, and more than just your radio itself. And general dangers, there's no well-documented source of danger. They're pretty low energy, and that can be kind of thought of because their general size, so because their wavelengths are so large, we tend not to see then a whole lot of energy occurring for these, all right? Because their wavelength is so large, their frequency is very, very low, right? And so as a result, they have generally, a high frequency wave tends to have more energy behind it. Next one we're going to look at is microwave. So microwaves, roughly 10 to the negative 2 meters, or if you're thinking general scale, 2 to 3 centimeters. So, roughly speaking, it could be, depending on the size of your fingers, about the width of your thumb, maybe 2 of your thumbs. That's generally the length of a wavelength for a microwave. Real common uses, cooking, mobile phone signals, right? So mobile phones will use a combo of some radio waves or signals for communication as well. So that's one of the uses. And then radar. We'll sometimes use those as well. Shortwave antennas, small antenna, things like that. Made by magnetrons, so microwaves, that the actual tool that they have, you can see in the diagram in the upper right, in which it generates these, and then transmitter too, like cell phones, all those things. What your microwave does is it focuses them on a specific point, similar to the idea of if you could take a magnifying glass or a lens of some sort and focus light. It's a similar thing, but this case with microwaves, not visible light, and that will focus that energy, and that's why it heats up your food. So dangers, staring at microwaves can cause cataracts in our eyes, right? Now, when I say microwaves, I don't necessarily mean the actual appliance in your household. I mean direct exposure to those microwaves. Your microwave itself is shielded and is also a big reason why it doesn't operate if it isn't closed as that part of that feature. So no, you're not actually going to get damaged by doing that. Having said that, I usually don't like to just stare at the food when it's in the microwave. I don't know about you. Whenever I put something in the microwave and that timer's going down, I got to finish a task. It's like I have a mission and I got to finish it before the time runs out. I go all Mission Impossible. All right. And also prolonged phone use can generate heat, right? So if you have that, your phone's heating up as a result with some of these things. And that actually, you can see those thermal effects here on this image, in which you can see before and after using the phone. So you can sometimes know that if you talk on the phone, right, your phone will get, or that side of your face could get warm. Sometimes people like sweat on their phone a little bit, which is kind of gross, but absolutely true. And this does lead us to our next wave, and that's going to be infrared, which is how the previous image was generated, and the one on the right. And so our size here, we're starting to get real small. So 10 to the negative 5th meters. All right, so real small, okay, as you can see. So about 0.00001 meters, so very small at this point. And a real common use is any remote control for like a television, a speaker, any of those types of things frequently uses infrared. There's some phones can use that, and a lot of times those you'll see on like their spec sheet something called an IR blaster, which is just a fancy name for a sensor that can push out infrared signals. Heat lamps will do this because they are very good at warming. Night vision will do this because it's really sensitive to thermal energy. And then weather forecasting will frequently use that to help generate the different radar you might see with some of the colors and things like that. You can use some of those for those. So hot objects are the big thing. So stars, lamps, flames, body temperature, really anything that gives off heat gives off infrared. So you're giving off a whole bunch of infrared right now because you have a regulated body temp. You produce a body temperature. We just can't see it unless we use specialized equipment. Dangers, overheating, right? If you're exposed to infrared too much, as you said, we could use it for heat lamps. That could cause problems, right? And so that's kind of really the biggest issue with infrared potentially. Next one, visible light. This is the one you know the best because that's how you're watching this video. You're looking at your screen and you're getting visual information, so you're able to get that info. This is how we interact and see with the world. Now these, we're getting small, 10 to the negative 6, those smaller than those microwaves, and the general range that we see is 400 to 700 nanometers. So basically our slice of the world that we see can be contained in a range of 300 nanometers, give or take or so. That's a really small sliver that we can actually see in the world, and it's kind of for the best because, as you'll see, there's a whole bunch of stuff going on, and we would probably be just completely overwhelmed and not able to process all that information if we were trying to see all of it. So common uses, visible colors, right? A lot of our electronics, anything that has a screen is utilizing visible light. Lasers that we can see, absolutely, right? If you get your cat to chase that laser, good fun use of a visible light. Printers will use that. CD and DVD players will use visible light to pull information, and along with magnets and things like that. Made by the sun, right? And really any form of technology we have, and will generate that. Dangers, you could have potential eye damage, right? If you're staring at the sun, not good, don't do that. Or if just things are really bright, or they talk about the stress in your eyes from a lot of blue light. I know in some classes I mentioned that idea of strains your eyes, right? Just like if you're looking at a screen a long time, your eyes get really tired, sometimes they'll get really red, and that is causing stress on your eyes, absolutely. Not that that's gonna instantly make you go blind, but some people think, potentially it can cause your eyes to age quicker, and so finding ways to filter some of that in some of the technology, having blue light filters, whether it be in glasses and screens and that's why that's becoming a lot more common in those as we kind of learn more about the stresses a lot of these screens can put on our eyes. All right, UV light, also known as ultraviolet. All right. It's just very frequently abbreviated to UV. General range 10 to 400 nanometers, about 10 to the negative 8th meters. And so that one gets really close to our visible range, not quite, and then can get a little bit smaller. We can use black lights to see those things. Common uses, sometimes you'll have like decor on them. They'll be kind of a fancy piece there. Tanning beds will use these. We can sterilize equipment with them, with these UV lights, because it's very good at killing microorganisms. And it's important in the production of vitamin C. So like you get UV light from the sun. You can go outside and that can be really good in small doses. But as you know, if you get too much, we can get, let me get to the dangers here, sunburn, right? And we all know that probably all too well because we've either been burned ourselves at one point or know someone who's been burned pretty bad, and it's not great, and that can lead to skin cancer. And of course UV light, if you're like actual direct eye exposure, can lead to blindness because it's basically a much more powerful version of visible light, much higher energy because we have a much higher frequency because that wavelength is so much shorter. If I didn't mention earlier, as our wavelengths get smaller, our frequency is going up by a lot, and as our frequency goes up, the pattern basically is the higher the danger, the more damage it can do to us. And it's made by sun, artificial lamps, a lot of those things. You'll notice a common theme, suns and stars. Well, our sun being a star produce pretty much all of these things. X-rays. So we know these, right? So their general size 10 to the negative 10th meter. So we're getting really small. Uses in like security, also medical fields, right? I'm sure a lot of us have had some form of X-ray at some point. Again, made by stars or machines that focus electrons. And of course, dangers could be cell damage. Now, when we're talking, so if you've ever had an x-ray, it's usually really short, right? You go in, there's a little buzz, and then the x-ray's done. It's very, very quick. That level of exposure isn't going to do anything. It's if it got turned on and was a very much longer repeated exposure, yeah, you could absolutely have some, significant cell damage for sure. Now, how an x-ray actually works is, as you see, that wavelength, I mean, it's tiny. These waves are so small. They pass through your skin. They just pass straight through your skin, but they can't effectively pass through bone. And that's why that's the only thing that's left, because your bone, thankfully, is a lot denser and more rigid than all of the rest of your body and your skeleton structure. So that's what's left, and that allows us to find gaps and breaks, because those, if we don't have any of that light bouncing back, which is how photography works, is light bounces back and we input that information. The x-ray basically is a photo that has very powerful light that penetrates through our skin and our muscles and all those things. It bounces back, and we're left with just anything that was denser than anything that's about the same density as bone. So it's a pretty neat little trick to be able to see, did we have a break or not? And it could also, again, because cell damage, generally when there's significant cell damage, that always increases the risk of cancer. And the last one is going to, for us, here I'll kind of move so we can see a little more of this diagram here, is going to be gamma rays. These are the ones that always get the glory in Hollywood because they're the most powerful and dangerous, and the ones that when we say radiation, everyone thinks of because they think radiation, that's going to kill me, and that kind of is true, but radio waves are a form of radiation, as they're named very similarly. But radio waves don't really pose any danger to us. Now, we have those gamma rays, 10 to the negative 12th meters. That's super small, right? Very, very, very tiny. And we can use them in radiotherapy, which is good for cancer treatment, mapping cell activity. Again, stars make them, right? And radioactive substances. So radioactive elements on the periodic table, which we'll spend some time later in the year learning about, absolutely produce some of these gamma rays, and they absolutely are very dangerous. Gamma rays are for sure super dangerous. They cause mutations and cell damage because these will actually go and alter the physical DNA of our cells. Because they're so tiny, they can actually interact with the DNA of our cells, which is crazy. And whenever you're messing around with DNA, you increase the chance of cancer because it can cause mutations to occur, which can lead to, runaway growth, which is effectively a cancer. The image on the bottom right, just to kind of point your attention there, you don't need to know the idea of alpha, beta, and gamma particles and things like that. But the idea being is gamma radiation can penetrate pretty much everything. We need to have special types of insulation so to make sure that we are shielded properly, because they can fairly effectively, easily pass through paper, pass through our bodies, pass through a steel plate, a lead plate. Lead does hold a little bit of that, so we need to have a lot of different ways to insulate, to protect those things and those radioactive materials to make sure they don't harm us. So we have special containers, typically lead lined, among other things, to help protect us from those. So a quick little summary here before we wrap up. We have kind of above, so really this shows us a whole bunch of things. So you'll see above whether it passes through our Earth's atmosphere or not, so like radio waves do, microwaves do not, visible light and infrared a little bit, absolutely. And then everything after visible tend to get blocked a little bit. Now ultraviolet does come through to capacity because that's how we get sunburn, so there's little bits, but not a lot of it is actually filtered out, which is really good because without our atmosphere, we just get roasted. All right. Radiation type, again, we have those all listed out for you. Proximate scale. So if you kind of want, well, what's a good estimate? So like radio waves, we're talking like buildings. Microwaves, think of like a butterfly, a smaller butterfly, not a huge butterfly, right? So as we kind of go down the line, we see those general, again, waves of frequency. You'll see as that frequency number gets bigger, so you can see like gamma rays have that frequency of 10 to the 12th, which is an absolutely massive number. That's the number of waves that happen in 1 second. That's crazy. That's huge. Super high energy. And then, of course, the temperature which the objects give this radiation off. So again, generally, the hotter the object, the, 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 And as we look at our table, so now we've gone through all these things. So you should be able to look at this table and recognize all these things, what they are, where their place is, and we're going to continue applying some of these things. And the next thing we're going to look at is what happens when we bend light. Well, how does that work? How do we predict it? And how do substances interact with these electromagnetic waves? If you have questions, let me know. Thanks for watching.